Hello and welcome to my YouTube channel. Today we are going to talk about the different types of materials available in the nature and what are the different energy levels associated to those materials. So let's start the video. In the previous lecture, I talked about the periodic table and we discussed about the semiconductors which fall under group 4, the dopants which fall under group 3 and group 5. So here we have semiconductors and group 3 and group 5 generally provide the dopants for the semiconductor. Now let us move ahead and talk about the energy levels associated to these atoms in the group 3, 4, 5 or any other atom in the periodic table. First of all, remember when we say energy levels, these energy levels are discrete and they are generally described by the number of their quantum states. So, every atom can have X number of electrons and those electrons will be having a type of shell associated to them. For example, we can have S, P, D or F type. Remember, when we say S type, then we can have maximum 2 electrons associated to any S. For example, 1s, 2s, 3s, 4s and so on. In each S, we can have maximum 2 electrons. Similarly, in P, we can have maximum 6 electrons. In D, we can have maximum 10 electrons. And in F, we can have maximum 14 electrons. Let us take an example and understand this concept a bit more. For example, silicon has got 14 electrons. Okay. And if we associate all the S, P, D and so on with the silicon, then how can we find how many electrons have been provided with which kind of shells? For example, 1s will take 2 electrons, 2s will take further 2 more electrons, 2p will take 6 electrons and then we can have 3s, further 2 electrons and last we can have 3p, but it will not take 6 electrons as usual, rather it will take only 2 electrons because 2 plus 2 plus 6 plus 2 plus 12 is equal to, we have taken all the electrons and we have filled all the S, P and shells of the atom. So in this way, so we have 2 electrons in the outermost orbit of the silicon and we have further 4 electrons vacancy. Okay, so 4 electrons vacancy is still available. That means silicon can take or give 4 electrons to complete either the P or it will take 4 electrons to neutralize itself. Now, let's talk about the energies associated to them. Remember, energies are in quantum state, so they are discrete, first thing. Second, they are provided by these quantum numbers 1, 2, 3, 4, 5, 6, 7 and so on. So in each row, we have these energy levels. So higher the energy level, the higher the row or higher the orbit the electrons will be situated. Now, the energy levels rise upward. That means this level has the lowest energy. So, electrons which are revolving in the 1s will have lower energy compared to the electrons which are revolving in the 5s. Although both are in s, but 1s will have lower energy, and the higher the row, higher the energy associated to them. Similarly, we can make a list as shown in the text box: 1s, 2s, 2p, and so on, 7f, and further more, depending on the number of electrons associated with any atom. So now coming to the types of solids. Remember, in nature, we can have three types of materials, or there are materials in three different states. One is solid, then liquid, and gas. Here we are focusing on the types of solids. The solids can be classified into further various types based on the arrangement of the particles, for example, atoms, ions, or molecules associated to those particular solid. So solids may comprise of different atoms, similarly maybe ions and molecules, and based on their arrangement, these solids can be classified. So generally solids are classified as crystalline solids, amorphous, ionic, covalent solids, molecular solids, metallic solids, or composite solids. Now in this course we are not going to talk about all the other solids, but we are going to focus only on these two types of solids, which are crystalline and amorphous. So crystalline solids, these solids are classified by the type of arrangement of the particles in them. Remember, these solids constitute particles, and these particles in case of crystalline solids are arranged in a regular repeating pattern in 3D, and we call these patterns crystal lattice. For example, salt, the natural salt in our home, is a crystal. Diamonds, quartz, and many metals fall under this category of crystals. Some of the properties associated to the crystal type of solids are that they have very sharp melting point. Sharp melting point means they generally melts at a very particular temperature. Maybe, for example, if a material or a solid is melting at 2014 degrees Celsius, then it is having a sharp melting temperature. Whereas many materials may melt in a range of temperatures, and they are not generally crystals. And these crystals generally have a very well defined geometrical shapes. So even if you break them, you will find that each particle which is broken down, they have a well defined geometrical shapes associated to them. Then comes amorphous solids. In general, amorphous solids have particles, but those particles lack a regular and repeating arrangement. So they have, we can say, a random kind of arrangement which are not regular in nature. So remember, particles inside the amorphous solids are arranged in a random manner. Some of the examples are glass, rubber, and plastics. They have amorphous behavior. What are the properties of amorphous solids? They often lack distinct melting point. So plastics may have a range of temperatures in which they generally melt. So amorphous solids have a range of melting point. They don't have a distinct melting point, and generally they soften gradually on the range of temperatures. So if you keep on increasing the temperatures, you may find that these solids often gradually softens with respect to temperature. So in general, we can see crystals like this. They have a very regular arrangement of atoms, molecules or ions. So they have very periodically arranged molecules, atoms or ions in them. But in case of amorphous solids, the arrangement is totally random in nature. Now coming to the crystals. Crystals have a highly ordered and repeating three-dimensional arrangements of atoms, ions or molecules. And we have defined that they have a property in which these crystals are generally having a very well-defined 3D geometrical shapes and a sharp melting point. Some of the examples are, we have discussed salt, diamond and quartz. Similarly, we have another type of materials which are called polycrystalline materials. In these materials, they have multiple crystal grains. They don't have a single type of crystal grain, rather they have multiple crystal grains. Each crystal grain can have their own crystal lattice orientation. So for example, here you can see there are 3 or 4 different colors associated to the crystal lattices, and they have a certain pattern, but overall these polycrystalline materials may contain multiple crystal grains and they have their own crystal lattice orientations. But these grains are randomly oriented. They don't have a very periodic arrangement of crystals inside them. Often these materials are resulted from solidification of molten materials or sintering of powders. Like amorphous solids, these polycrystalline materials also don't have a sharp melting point. So they have a range of melting point, and they often soften over a range of temperatures. So they have a more or less similar behaviors compared to the amorphous solids. Some of the examples are, most of the metals, they fall under the category of polycrystalline materials, and ceramics, they also fall under the category of polycrystalline materials. And like we discussed in the previous slides, amorphous solids, generally they lack a regular and repeating structure. So they don't have a regular or repeating structure. We can see from the diagram here on the top right that the atoms, ions or molecules are arranged in a random fashion. Formation. These materials can result from rapid cooling of a melt or deposition from a vapor phase. Properties we have discussed in the previous slide. They lack a distinct melting point, and often they soften gradually over a range of temperatures. So they don't have a sharp melting point, and they softens over a range of temperatures. They include glass, rubber, and some plastics. With this, I would like to end this presentation. If you have any doubts or suggestions, please post your doubts and suggestions in the comment section. If you have not subscribed the channel, then I would request you to subscribe the channel. Thank you and have a nice day.